Hi guys, welcome to this session on work done. So work done is a topic that's mentioned in P1 to do with energy and also in P5 to do with forces. So what we're going to do is we're going to look at what work done is, and we're going to identify where situations where work is actually done, and we're going to calculate work done. So what is work done? The best way to think about it is we look at the picture on the bottom left. This guy is lifting up a dumbbell with his bicep, doing a curl. So what he's doing is he is applying a force there to lift that dumbbell up. And what he's also doing is he's transferring energy to that dumbbell. So look back at different types of energy. What they're actually doing is they're converting chemical energy from using their cells of respiration. They're converting it into kinetic energy, and then they're converting that kinetic energy into gravitational potential energy. So this is essentially what work done is. Work done is energy transferred by a force. Now it's when the force displaces the object, i.e. it moves it from one place to another. So there are some other examples of work done here. The bottom left, that child is pulling along the sledge. He's applying a force to the sledge, transferring the kinetic energy to that. You could even argue as well, if he pulled the sledge along, that sledge has got kinetic energy, and the force of friction is doing work on the sledge there. There we go. The force of friction is doing work on the sledge there, and that friction is causing the kinetic energy to be turned into thermal. Hence, he's trying to slow it down. That thermal energy will then increase the temperature of the snow against the ground and of the sledge. Another example of the classic one, which is just related, if you like, to the bicep one, is going upstairs again, converting chemical to kinetic to GPE. You're doing work against gravity there to go up. We've got some other examples here. The trolley, again, very similar to the second one, but the book on the table, some people do think that is work done. And I understand why, because they say, well, the force involved, you could argue there are forces, there is weight, and there is also the normal reaction force of the table acting on the book. And they could argue that the book has got GPE. But remember, work done is energy transferred by a force. There is no energy transfer in this situation at the minute. The book is not moving, it's not being displaced by any force, therefore no work is being done. The same goes to the person sat on the chair. So let's look at these two situations here. So you could even say that if you had a ball falling, so the opposite, that gravity is doing work, it's transferring energy to the ball, and this time the energy is going from GPE into kinetic energy. And the car is moving, and then the brakes are applied. So in this case, the force is friction, and that friction will turn the kinetic energy into thermal. What we say is that heat or thermal energy is being dissipated, or energy is being dissipated as heat. Dissipated means that energy is transferred from something to a non-useful store, i.e. heat. The brakes in this case get quite hot, which can be a disadvantage because the hotter they get, it means that they won't be as efficient as working. Hence why some cars have ceramic brakes, as they're very good at cooling, they won't heat up, so the car will be very efficient when it brakes. Now, I said about work being done, energy transfer from one form to another via a force. We can talk about work being done, though, in this case. So in this case, we have electricity, and that electricity is going to be transferred into a couple of different types of energy. It's going to be transferred into kinetic energy, and it's also going to be transferred into thermal. Now, this here is not done by a force, but it is done by a current. So work can be done by a current rather than a force. Some people might be asking, well, surely in this case, in a hairdryer, you also get sound made as well. The sound is probably caused by things like friction. So what will happen is some of this kinetic energy will have friction acting on it, and that friction will do work, turning it into sound and probably even more thermal. So work can be done either by a force or by current. So here we go with the car, moving along. If you look, the store of kinetic energy decreases and the store of thermal or heat energy increases. And you can also see that my PowerPoint skills are not perfect. Cheeky. Okay, calculating work done. So this is an equation that you need to remember. It's not given to you, and it comes in handy quite a lot. So work done is force times distance. Distance measured in meters, force measured in newtons, and work done in joules. If you're going to be lazy, joules capital J, newtons capital N, both of those are names, so capital letter, meters little m. These are the symbols for it. You don't have to use the symbols, but just in case you wanted it, that's how you write it in symbols. So here are some questions. If you'd like to have a go at it, then have a go, and I'll pause and I'll reveal the answers. Okay, here we go. Nice and easy, these ones. Just got to change a few things. Kilometre, it's 1,000 meters, so multiply that by 1,000 straight away. Kilojoules here, so 1,000 joules. One thing I just wanted to relate it to was this earlier picture here. So if you have a ball falling, we talk about work being done. Work done is force times distance. Now, if we're talking about the force in this case, the force in this case is actually weight. So it's going to be weight times distance. Now, if we look at what work done is weight times distance, but weight is mass times gravitational field strength. And the distance in this case is actually going to be the height that the ball is dropped from. So now you can see that work being done is equal to mgh, and that looks very, very familiar. That is gravitational potential energy. So what we're trying to say is that this is how we get gravitational potential energy, because we're doing work against the force of gravity, against the attraction due to gravity, and we're causing energy to be transferred to it. So hence, when you move an object up, we're storing this much energy in. And then if we drop this object, we're turning this energy into kinetic energy. And this equation, therefore, is incredibly similar to this one. It's the same thing, pretty much. Now, comes to this question. This is a little thing that's on the specification that some people gloss over. What is a joule? Well, this is where we use the equation that we had earlier. So work done is force times distance. Now, if we look, work done is measured in joules because it's just energy transferred. So if I had 1 joule of energy transferred, what force would I need to do it? What distance would it need to be over? Well, it's quite simple. If you wanted an answer of 1, you make this number 1 and this number 1. So if you wanted 1 joule of work to be done, you need a force of 1 Newton moving an object by 1 meter. So that is what a joule is. It's where 1 Newton of force acts on an object for a length of 1 meter, and it's how much energy is transferred in that time. So we could actually rewrite this. We could say that a joule is also the same as 1 Newton meter. This is something that can come up, and what they might do is, instead of telling you that work done is measured in joules, they might actually tell you the work done is measured in Newton meters. It's something that might catch people out, but a Newton meter is exactly the same as a joule. So don't let it catch you out. Okay, if you want some more practice questions, here you go. I'll reveal the answers in a second if you want to pause away. Okay, here are your answers. So this question relating to the car, when you've got a car moving, you have got to do work onto the car by friction in order to stop it. So you've got a choice. Either you need a high force and a low distance, so you put the brakes on really abruptly and you stop very quickly, or you put a low force on over a longer distance. So obviously, if you have something like a car crash, the reason why hitting something like a tree or a wall is incredibly painful is because you're stopped in a very short distance, therefore a massive force is going to do the work. But when you're driving on nicely, you're always told that you need to put your foot on the brake gently so that you've got a small force acting for a longer distance. In both cases, the work done is exactly the same. Now, very interesting question that comes up in exams here is to do with the work done. So if you imagine I have got, I don't know, a person here of weight W. That person is walking up the stairs and it says, can you calculate the work done against gravity? Now, this is a real tricky one because people know that the force is going to be weight, but they're really unsure about what distance to use. Could it be D? Could it be H? Could it be D plus H? Could it even be something like, I don't know, maybe this is a triangle, and actually what we're going to do is do a bit of Pythagoras Theorem, and we're going to do h squared plus d squared and then root that. What is it? Well, we're doing work against gravity, right? So work done against gravity only happens in the vertical direction. So when we're doing force times distance, it's only going to be this force times this distance. Technically with D, what you're doing is you're also doing work against friction because you're pushing yourself towards this way by applying a force against the surface of the stairs. So look at what the question says. If it says, well, doing work against gravity, then you only need the height. Okay, that's it guys. Enjoy. See you next time.